VT is 25 millivolt that we have been using. So look, this IC is the current, follows this relation, which means that it is a function of VBE. It is a function of VBE, and you actually did one pre-lab pertaining to this equation. So that's why this IC is a function of VBE. So therefore, IC can be replaced with a current source. IC could be replaced with a current source, which is basically I'm going to talk about this in a moment. Transconductance and as a function of VBE. So this is transconductance, and I have this. You don't have to write it down for the moment. I have this defined already. So the reason I'm writing here is that this is voltage-controlled current source. So you can model this transistor as voltage-controlled current source. It is current. It is controlled by the voltage between base and resistor. Okay, and it is coming from this Shockley equation. So this equation is important because you're using this equation is solving many problems. This equation is very important. And I have actually written this equation right here. Okay. So the transistor has to operate in active region, and then the other important keyword here is linear. So far, we did not talk about linearization at all. Okay. The transistor is a nonlinear device. It's a nonlinear semiconductor device. But we are going to use this transistor as a linear amplifier. We are going to use this transistor as a linear amplifier. Yeah, try to understand here. Now, what we need to do, you remember that we had this op-amp, we had some DC sources. We had some DC sources here. So VCC, VEE, right? Plus minus 7 volt you provided when you did your first laboratory assignment. We don't need these DC sources to actually bias the transistor. What does that mean, bias? Bias means that we need to make sure we provide DC sources, we chose resistors for the circuit with transistor to operate as an amplifier. We chose resistors, capacitors, we chose some voltage sources in such a way that we need to make sure that the transistor operates in active region. So we first make sure that the transistor operates in active region by providing DC sources. By providing DC sources, and we'll choose some resistor network. Once we decide, once we know for sure that the transistor is operating in active region, then we mess it with amplifying like small signal. Then we deal with our not before that. So once we find the operating point, the bias point means IC and VBE. Once we find this coordinate, IC, VBE, IC, VBE, comma, IC. This is one point, and IC, VCE, comma, IC. Okay? So this is another point. Once we find these points, based on the resistors and DC sources that we apply, Then what we are going to do, we are going to linearize the input-output relationship around this operating point. Now you need to know a little bit of math here. So let's say you have a function. So this is f of x. This is f of x. So this is f and this is x-axis. So this is function. This is a function of x, and it's a nonlinear curve. Now what you do, we find a coordinate right here, and this coordinate, let's call this x0. This is basically, we are calling it operating point. So this is x0, this is x0, and here this point is f of x0. What we are going to do, I'm going to use blue. We are going to vary this x around this point. So around this operating point, this transistor is going to be operating just like a linear amplifier. So we will be operating the transistor around this operating point, and this point is found using DC sources. This point is found using DC sources. That's why in op-amp you see that VCC and VPE, you have to supply two DC voltage sources. You have to apply DC voltages in two different points. So here we are going to use Taylor series to linearize. How do you do that? So f of x can be written as f of x0 plus partial f over partial x, and you evaluate it around the operating point x equals x0, and you take the difference x minus x0 plus partial squared f over partial x squared, 1 over factorial 2 factorial, and then you evaluate that at x equals x0, and then times x minus x0 squared plus higher order terms, okay? Higher order terms. This is simply a Taylor series. So we actually approximate this function as such. Now, what does that mean, linearized? When I say that transistor is linearized, which means that we remove all the inputs, we just keep the DC sources, and based on the DC sources and resistors, we find the operating point, which means that the collector current and the base emitter voltage, collector current and collector emitter voltage. So we find this operating point, and then around this operating point, the transistor operation is going to be linear. So you will see how this is applied in a moment. We are going to simply discard this higher order term. Here it is going to be simply, this part is B, this part is delta x, and this part is your M. So it's going to be y, approximately y equals m delta x plus b. So this is linear. this is linear. This is simply a straight line. So where this M is slope and B is intercept. B is intercept. So this is just the basic idea, and we will be directly applying this Taylor series in the coming slides. So, and that's what it means, linearized. So the current voltage behavior has to be linearized around bias point, or it is called operating point. Operating point, and people also call it Q point. Same. Okay. So again, this is NMOS voltage amplifier. What we are going to do? We are not going to cover this. NMOS voltage amplifier, we are not going to cover anything pertaining to NMOS in this model. So we'll just focus on NPN voltage amplifier, which is right here. So this is the most basic version. This is the most basic version of NPN voltage amplifier circuit. By the way, so we'll get to the point where, look guys, we'll get to the point where this circuit, just try to understand guys, and try to just note it down. This circuit, see, gradually, how this circuit becomes complicated, and we will get to the point. We'll get to the point where that circuit becomes this one. Okay? See the steps. If you miss some basic concept, then you will not be able to understand this circuit. This is where we are getting, and you would be implementing this circuit using PSpice only, and that is the required for the last level to SML. Okay? So no actual experiment using breadboard. Just forget this part, that's it. And we will be covering this part. This is where we are getting. So try to understand from the beginning how the operating principle of NPN PVT voltage amplifier. So here, we are providing some input, and this input, okay, another thing very important, and it's going to be very confusing, guys. Please try to note it down. The symbol. So here, V here, do you see that V is lowercase? And you have subscript, you have uppercase, right? The convention here is that when you have the signal lowercase with subscript uppercase, which means that this signal contains both AC and DC. So this signal basically contains DC plus AC component. So this signal contains both DC and AC components. And when you have this uppercase symbol, uppercase letter with uppercase subscript, so this is DC only. And this signal, again, this signal, what do you think about this signal? This is going to be lowercase b and uppercase subscript ce. So DC plus AC. So please don't get confused. If you don't know right from this point, then you'll be confused in the upcoming lecture, upcoming slide. Okay. So now the voltage transfer characteristics, if you plot VBE and if you plot VCC, so this is y-axis, VCC is the output we are taking from the collector terminal with respect to ground, which is connected to the emitter terminal. This is going to be the voltage transfer characteristics. So as you can see, when VBE is 0, look guys, when VBE is 0, you do not supply any voltage. Okay, do you think that this transistor is going to be on? It's a base emitter voltage is less than 0.7, right? And base emitter, you can think of this as a diode, less than 0.7, therefore this transistor is on. So you can just think of this transistor as an open circuit. Then the voltage of this point, no current would be flowing, voltage of this point is going to be just VCC. And that's why you see that when VB is 0, the voltage is VCC. Now, as you increase VB until certain point, here, author gives 0.5 as the on voltage, but what I'm going to do, all my examples, even in the example, default terminal voltage for diode is 0.7. Even if I don't mention, please ask it. Okay. Default terminal voltage is 0.7. But for different transistors, for different diodes, you may have different manufacturers provide different terminal voltage. But for my case, the default terminal voltage for diode is going to be 0.7. So all the way to 0.7, and then this transistor is on, and transistor is going to enter into active. And at some point, when VBE is more than certain voltage, so transistor is going to enter into saturation. So this is the region that we are interested in. And in this region, you will see a steep slope like this. Steep slope like this, and this slope actually determines the gain of your transistor. This slope actually determines the gain of the transistor. This slope determines the gain of the transistor. The base resistor, bias resistor RC, this bias resistor RC converts the collector current into output voltage, as you can see. And then output voltage, this output voltage is VCC minus whatever current is flowing times this RC, the voltage drop factor of this RC. So here, this is going to be VRC. So you just deduct this, the voltage drop, then you get whatever the difference you have. And then I have just reiterated here, amplification occurs when BJT is in active region, and it actually satisfies this relationship. So here, the gain of the transistor is going to be the slope that is determined D. So let's now move on again. So this is using NMOS for the exam purpose. You may want to just omit that. You may want to omit this NMOS amplifier. I'm not going to cover the NMOS just the BJT part, again, this part. So we are coming to linear amplification by NPN transistor biasing. Now, linear amplification by NPN transistor biasing, which means that we are going to bias the transistor first. Biasing means we just try to find the operating point IC, VCE, IC, VBE. These values, we are going to find these values using DC source only, omitting all the inputs, omitting all the inputs. So for that, we are going to assume that for transistor amplifier, it is going to operate in active region, which means that VC is greater than VB and VB is greater than VE. VBE is going to be approximately 0.7 volt, and IC is going to follow this condition. So the transistor will be operating in active region. These are the conditions. So base emitter junction is going to be forward biased, and base collector junction is going to be reverse biased. So because we will be biasing the transistor, that's why all the sources will be DC only. So as you can see, this is VCC, all uppercase, DC component, and this sources is going to be DC component. This source is DC only. So the DC voltage VBE approximately 0.7 volt, which will turn on this transistor, makes this transistor to operate in active mode. This sets the bias point, which means IC and VCE. See, VCE, comma, IC. This is one Q point. This is one Q point, and another Q point is for the input output characteristic voltage controlled current source. So VBE, comma, IC. This is also Q point. Here in this slide, because we are saying IC and VCE, so these 2 points under active region, the value of IC and VCE will be your Q point. So the operating point is referred to as Q point. And when transistor operates in active mode, the bias point satisfies this condition. The bias point Q will satisfy this condition. So this VCE is going to be VCC minus ICRC, and IC has to be equal to beta IB. So when you bias the transistor, omitting all the AC sources, AC signal, just the DC sources, then it has to satisfy this condition. So that way we get this value here, which is the X component of this Q point, and IC is the Y component of the Q point. Now, before I do that, so this is not in the, actually we covered it in BJT. In this chapter, you don't see this plot. So make sure you remember. So you have IC and you have B, C. You have IC, you have VCE. Now, when you do not have any voltage applied, I'm just going to read what the transistor here. This is C, this is E, this is B. Okay. So when you do not have any VBE voltage, which means that no current is flowing right here. IB, no current is flowing right here. So that time you have, this is cutoff region. So no IC. So this is cutoff. And in cutoff, which means that base, collector, and emitter. No connection. Cutoff means when you do not have any VBE, IC is going to be 0. If IC is 0, you can think of this transistor 3 terminals just open. As simple as that. So this is your B, this is C, this is E. Okay. Now, as you apply some VBE, therefore some current IB is going to be flowing. So you will start seeing a curve like this. Okay. So here you have IB certain value. Here you have IB certain value, and this is IB certain value. IB for different IB and different IB. Okay. Now, when IC is 0, when IC is 0, which means that the current flowing through the collector terminal is 0, the VC is going to be just VCC. So this is going to be VCC. And when VCE is 0, which means that it is going to be simply short, that time you will see that the IC is going to be maximum right here. So this is going to be this is called load line. Okay. Now, as you keep increasing VBE, therefore you are increasing IB. So you will see different curves for different IB. Now, the point where it is intersecting, so you can take any of these intersection points. This is going to be your key point. Key point, which is VCE, comma, IC. This is your key point. And at this key point, your IC is going to be beta IB. So whatever IB you have, if you multiply with beta, it is going to satisfy. So this is going to be, IC is going to be beta. And this is the key point that we are talking about. Now, if you remember, guys, because there is no explanation for the negative side in the upcoming lectures, but just to give you some heads up, guys, look, we have inverting amplifier was like this. So this is input. So this is R2, this is R1, and this is your output, V out. And this V out was negative R2 over R1 times VE. You remember guys? The inverting amplifier that we went through in our in chapter 2, in module 2. So we have this negative, right? Where does this negative come from? This negative will come from, this negative is coming from right here. You see, we said that in our, operational amplifier, we actually zoom in what's inside this operational amplifier, right? And we have transistors, BJTs are there, we have resistors there, we have voltage sources there, we have capacitors there, okay? So we have all these components. Now, that transistor has certain characteristics where if you provide input, if you provide more input, the output is going to be just the opposite. Output is going to be less. If the input is less, output is more. So the operation is just reverse. And that is the reason you will see negative in the upcoming slides. So what you have here, yeah, please pay attention. Okay, so here you have certain IB, and this IB is more than this IB. So you have VBE, IB1, so that corresponds to VBE1, and IB2, which is greater than IB1, and which is, that corresponds to VBE2, which is greater than VBE1. So this VBE is going to be more than this VBE1. That gives you a certain current. All right. So now what you want to do, okay, look, what do you see VCE here? You have small VBE, you have more VCE, right? Right? Small VE, but VCE is more here. What about this point? You have more VBE, but you have less VCE. Do you see that? Which means that the voltage between collector and emitter terminal, VCE, this voltage is decreasing as you increase VBE. So you increase VBE, but VCE is coming down, is decreasing. And that is the reason you will see negative in one of the equations, output equations in one. Okay? So because we are increasing VBE, and that actually decreases VCE. And that is the reason you will see, this negative in the output. All right. So now let's get to the main point. where we actually combine DC and AC signal. So here, lowercase b and uppercase be. Here you have uppercase b, uppercase BBE, which is this is DC component, and this is basically what is this, guys? You see, all lowercase, right? This symbol? No, this is all lowercase, which means that all AC. So here you have all AC, and only this AC component we call this small signal. Only AC component we call this small signal. Okay? So this AC, only this AC component we call this small signal. So this is, you have DC, you have AC. And then lowercase b and uppercase BBE is your DC plus AC. So please don't get confused with this symbol, okay? Make sure you know which one is a small signal and which one is the actual signal that contains both DC and AC component. Here, you see that AC component is denoted with this, and you have DC component is denoted with all uppercase. So therefore, the total is basically B, BE, T. So this is the total input signal. So DC bias voltage VBE sets the Q point. This VBE is responsible for setting the Q point, and the small signal VBE causes the variation in IC. So this current is going to be varied based on the small variation of VBE, hence VCE. So if you look at this load line, this load line will be going this way. This load line will be going this way and this way, depending on your small VBE. If VBE is more, this load line will go this way. If VBE is small, load line will come this way. You understand, guys? So this load line will be actually moving based on this small signal VBE. Okay? So now, all what we are trying to do, we are trying to first set this load line, first set the DC analysis, first biasing the transistor circuit so that we can get this Q point. Okay. So as long as the Q point remains in active region, the results in this results in linear amplification. So what we want to do, we want to make sure that this Q point, very important, guys. I'm going to use different color. This Q point should be in the middle. If you place the Q point in the middle, which means that we are sure that these operating points are in active region, but this Q point, if you chose this Q point close to this region, this region is called saturation region. Okay, saturation region is used for switching purpose only, but active region is used for amplification only. So we need to make sure that our Q point is in the middle, this region. We need to make sure the Q point is in this region, just like in the middle. So that's what we are trying to do here. So we have VCE, this output is going to be the DC voltage minus, now we are coming to the transconductance parameter. So GM is called transconductance parameter. GM is the transconductance parameter. So VCE minus RC, and this is basically current. And you will see this in a moment. So this GM is IC over VT. IC over VT is the transconductance parameter. And now how to get this part? And this is shown in the next slide. Again, this is small signal operation of MOSFET. We are not going to cover this part. We are not going to cover this part. And then we are not going to cover this part as well. No MOSFET part. No MOSFET part. No MOSFET part. No MOSFET example. We are coming right here. Based on the discussion that we had. So in the previous circuit we had both DC and AC, but for biasing purpose we are going to remove this AC component. So the AC component, we just simply remove it. If you see the circuit diagram, we have VBE. VBE is right there, and then VBE is connected directly to the base emitter terminal. So this is ground, and we will have certain ID, and we have this DC voltage. So BJT is biased in the active region using a DC base emitter voltage. So we have a DC base emitter voltage. That the collector current is going to follow this relation. We went through this relation previously. I already explained. And IC is going to be beta IB. And the collector voltage VCE is going to satisfy this relation. And here Q point here again, here Q point VBE IC is chosen such that VCE is greater than VBE minus 0.4 to ensure that it is in active region. In other words, VB with respect to ground has to be greater than VE, and VC has to be greater than VB. In other words, VCE has to be greater than VBE 0.7 minus 0.4, which is about 0.3, to ensure that the operation of this transistor is in active region for amplification. So I want to get to an example, but I need to cover this part before I go to that example, because if you don't know the small signal part, then it is going to be tough. Okay, guys, remember the total current ICT, total current is going to be the DC part plus lowercase IC, the AC part. So this is AC part, and this is DC part. So this total current is going to be DC plus AC component. And this total current satisfies IS times e to the VBET over VT. Now this VBET is basically, you have lowercase VBE, and you have this VBE. So these two part, this voltage is going to be VBE plus lowercase VBE. Okay. So this is the AC component and this is the DC component. You just add these two components, you substitute right here, then okay, so I'm going to write it in a different way. This is too short. So we have ICT, please rewrite guys, ICT equals IS e to the VBE plus lowercase b BE T over VT, which we can write it as IS e to the VBE over VT times e to the lowercase BBE T over VT. And this part is basically your IC. So you have IC times e to the VBE over VT. Okay, guys, do you remember what is e to the x? Do you remember, guys? What is e to the x? Series of e. You don't remember? 1 plus x squared over factorial 2 plus x cube over factorial 3. You remember now, guys? From math. Okay. So what we are going to do, we are going to linearize it. We are going to just keep the first one. So you see that it is IC plus IC times 1 plus VBE over VT plus higher order terms. So I'm going to approximate this by neglecting higher order terms. So if you just neglect this higher order term, you get this IC plus IC over VT times VBE. And you get this ICT is IC plus, and this is basically the DC component. AC component of the current. And this is called GM VBE. And this GM is basically IC over VT, and that's where it is coming from. Okay? So I actually directly wrote this GM, this transconductance parameter right here. So IC equals GM plus VBE. Now the small signal part, this is the linear term, and small signal part of the current, collector current, is I lowercase c, IC equals GM VT, and GM is basically IC over VT. Now the voltage gain is, this is where the negative sign steps in, guys. Negative sign that I was talking about. Why? In operational amplifier we saw negative for the inverting operational amplifier. So AB, voltage gain, which is CE VCE, and this is your VBE. So this is the input and this is the output. This voltage gain is basically output over input, and you get this minus from the characteristic curve that I went through just a few slides ago. So this negative is coming as VBE is increasing, VCE is decreasing. If VBE is decreasing, VCE is increasing. And that's where this negative is coming. Okay? So you have this negative GM times RC. If you just get this VBE and you get the VCE from previous equation, you get this voltage gain. This voltage gain is VCE over VBE, which is negative GM times RC. Now, as an exercise, you have GM equals partial T IC over VBE, and you have the GM equals IC over VT. What I did, I actually solved this exercise right here. So this exercise solution is right there. It's basically the one that I just wrote. You just take the partial derivative, or you can just expand E and take the first term, and that's how you get this GM. Now, in our next class, I'm going to stop right here because this requires a small signal component, and then I wanted to cover this example. Yeah, I wanted to cover this example. That example requires some small signal analysis. So I'm going to stop right here. I'm going to go through this small signal analysis in our next class, and then I will cover one example, then biasing, and straight to the amplifier. Okay. So today we have covered a bit of theory. Actually, just theory is boring. I know. So this theory is going to be helpful for the upcoming examples and simulation. Okay. So I'm going to stop right here because some of you probably are leaving. So have a safe travel, guys. Travel safe. Come back fresh for more challenges. Yeah, that's all. Happy Thanksgiving, guys.